I'm going to talk about the pre-treatment section for our simulation project. Okay, the first step is to register our component. So, which is PET. In PET, it consists of 75% ethylene, 20% propene, and 5% petroleum-derived aromatics. In this 5%, it consists of benzene, toluene, and xylene. Okay, after we need to register all these components into our system. So here's benzene, ethene, okay, ethene, xylene, and so propene and toluene. Okay, after done register all these things, we go for the next step, which is register a new stock mixture. Okay, we create a new stock mixture, and then add it. So in the composition tab, we need to key in all the composition, the percentage. So as mentioned before, ethene for 75%, propene for 20%, benzene for 1.67, toluene for 1.67, and also xylene for 1.66. Okay, after done register all these stock component, then we go for the process. In this process, our inlet assume that waste plastic always comes with dirt. In this case, our dirt we consider as water and sodium chloride. So that's why it comes with all these things. So in our inlet, we have 95% of PET, 3% of sodium chloride, and 2% of water. Then the unit is in mole per year. Okay, first it enters a storage tank. In this storage tank, we never include anything for thermal mode. We set it as adiabatic. This is to equalize our flow so that we get an equal flow. We further improves our process. Okay. After that, after storage tank, we go for belt conveying. In our project, we use belt conveying is due to because pump only can use for liquid and compressors for gas. For solid, we need to use belt conveyor to transfer all the reactants. Okay. After the belt conveying, we go for shredding unit operation. In shredding unit operation, we never really touch anything with it because all these things is set by we use the default setting from the Super Pro. Okay. So why we need to include shredding is because by theory, shredding you reduce the size. Then smaller size means larger surface area. And larger surface area means higher rate of reaction. So that's why you chose shredding in this. Okay. After it follows by belt conveying again. Then it goes to the next unit operation, which is washing. This is to wash out all the dirt from an inlet stream, we assume. Okay. In this case, we wash out 99% of the sodium chloride and 99% of the water. Which means these two is the dirt. Okay, how we wash it? We use the washing stream. In this case, the washing stream is S017. Okay, washing stream. Then what for the washing stream? We assume there is only pure water, which is 5,000 ton per year. Okay, after you wash out, it contains no more dirt. Then we go for belt conveying again to move the plastic, the PET, into the next unit operation, which is rotary drying. This is to further dry the PET into almost the moisture level to almost 0%. So that's why we set it here. Removal is set by user. Okay, water. Okay, removal of water is 99%. We set it as okay. How we dry it? By using air. Okay, that's why here there's one inlet stream here S111, which is the inlet air, in order to dry our plastic. Okay, all these things is calculated by Super Pro itself. Okay, after it dries, go for conveyor belt and it comes up with S113. Then S113 is the inlet for the process part. So that's all for the pre-treatment section.
Okay, I'm going to talk about pyrolysis section. For this section, the PET will be react with inlet, and then we will be getting syngas, which is consists of carbon monoxide, hydrogen, methane, carbon dioxide, and also nitrogen. And we'll be getting pyrolysis oil, which is the anthracene, and benzoic acid, biphenyl, diphenyl methane, as well as benzophenol, and also solid, which is the char, in this case, which is the carbon. And first, what we're going to do is actually to register the inlet which is the xenon, this one, and as well as the 5 component of the pyrolysis oil, which is anthracene, benzoic acid, biphenyl, benzophenone, as well as diphenylmethane. While for the syngas, we need to go to stock mixture and register a new mixture, which is the syngas. And under syngas, we need to include carbon dioxide, which is 11.5 mole percent of carbon dioxide, 22.2% mole percent of carbon monoxide, 10.9 mole percent of hydrogen, 4.5 mole percent of methane, as well as 50.9 mole percent of nitrogen. And then from stream S113, we'll be going to the electric heating, and the purpose of putting electric heating is because the stoichiometric reactor, the pyrolysis reactor, cannot reach the temperature of 350 degrees Celsius. That's why we need electric heating. As for going to the pyrolysis reactor, we need to put the inert gas, which is xenon, as in this case, which is 50 ton per year. The reason of putting inert gas is to stabilize the pyrolysis reactor, because the hydrogen gas is highly reactive. So we need at least 50 ton per year according to the inert of the PET, the amount of PET, and also 0.05% from the PET. And in this pyrolysis reactor, we need to set the extent to be 90% and to key in the stoichiometric reaction, which the reactant consists of PET and also the inert, which is the benzene and ethene, xylene, propane, toluene, and xenon for the reactant. While for the product, we will be getting syngas, pyrolysis oil, as well as the char, which is anthracene, benzoic acid, benzophenone, biphenyl, carbon dioxide, carbon monoxide, diphenylmethane, hydrogen, methane, and as well as nitrogen.
I'm going to talk about product separation section. First of all, link the top outlet of the pyrolysis reactor into the cyclone. In this cyclone, set the particle removal specification at 100% removal for the unpyrolyzed PET. The components of the unpyrolyzed PET are benzene, ethene, xylene, propane, and toluene. Next, the top outlet of the cyclone is sent to a condenser. In this condenser, the operating specification is set at condensation temperature, and for the component phase distribution, the gasified pyrolysis oils are condensed into 100% liquid phase. The components of the pyrolysis oils are anthracene, benzoic acid, benzophenone, biphenyl, and diphenylmethane. Next, the top outlet of the condenser is sent to a storage. The thermal mode of this storage is set at adiabatic, and the product of the storage is syngas. Syngas consists of carbon dioxide, carbon monoxide, hydrogen, methane, and nitrogen. The bottom outlet of the condenser is sent to a pump for further processing of liquid pyrolysis oils, and the bottom cyclone is sent to a flow splitter. Set the flow splitter splitting specification at 90% to top stream. The unpyrolyzed PET that are still in solid form are recycled back into the mixer to repeat the process, while the bottom stream of the flow splitter is sent into the solid storage together with the bottom outlet of the pyrolysis reactor, and the thermal mode of this solid storage is set at adiabatic as well. And the product of this solid storage is char, which is a carbon.
I'm going to present the product distillation section. The purpose of product distillation is to obtain purified benzoic acid, biphenyl, diphenylmethane, benzophenone, and anthracene from the liquid pyrolysis oil. Liquid pyrolysis oil will first emerge as the liquid output of the condenser and enter a pump to increase the pressure by 100,000 Pascal. The liquid pyrolysis oil will then enter the first distillation column. In the first distillation column, the purpose is to obtain purified benzoic acid. Therefore, benzoic acid was set to be the light key, whereas biphenyl was set to be the heavy key based on the boiling point. Benzoic acid was set to have relative volatility of 1.2 with 99.99% in distillate, whereby biphenyl, diphenylmethane, benzophenone, and anthracene was set to have relative volatility of 1, 0.8, 0.6, 0.4 respectively, with 0.01% in distillate. The distillate of the first distillation column, which contained pure benzoic acid, will enter a storage drum. The storage drum for benzoic acid was set to operate at adiabatic thermal mode, whereas the bottom of the first distillation column will enter the second distillation column to separate biphenyl and diphenylmethane from benzophenone and anthracene. In the second distillation column, diphenylmethane was set to be the light key, whereas benzophenone was set to be the heavy key. Benzoic acid, biphenyl, and diphenylmethane was set to have the relative volatility of 1.6, 1.4, and 1.2 respectively, with 99.99% in distillate. Whereas for benzophenone and anthracene, the relative volatility was 1 and 0.8 with 0.01% in distillate. The distillate from the second distillation column will enter the third distillation column to further separate biphenyl and diphenylmethane. In the third distillation column, biphenyl was set to be the light key, whereas diphenylmethane was set to be the heavy key. The relative volatility for benzoic acid and biphenyl was set to be 1.4 and 1.2 respectively, with 99.99% in distillate. Whereas for diphenylmethane, benzophenone, and anthracene, they are having 1, 0.8, and 0.6 as their relative volatility, with the same 0.01% in distillate. The distillate of the third distillation column, which contained biphenyl, will enter a storage drum. The storage drum for biphenyl was set to operate at adiabatic thermal mode, whereas the bottoms of the third distillation column, which contained diphenylmethane, will enter a storage drum as well. The storage drum for diphenylmethane was set to operate at adiabatic thermal mode as well. Meanwhile, the product of the second distillation column will enter the fourth distillation column to further separate benzophenone from anthracene. In this distillation column, benzophenone was set to be the light key, whereas anthracene was set to be the heavy key. Benzoic acid, biphenyl, diphenylmethane, and benzophenone are having relative volatility of 1.8, 1.6, 1.4, and 1.2 respectively, with 99.99% in distillate. Whereas for anthracene, it is having relative volatility of 1 with 0.01% in distillate. The distillate of the fourth distillation column, which contained mainly benzophenone, will enter a storage drum. This benzophenone storage drum was set to operate at adiabatic thermal mode, whereas the bottom for this fourth distillation column, which contained mainly anthracene, will enter its own storage drum. The storage drum for anthracene was set to operate at adiabatic thermal mode as well. For heat integration, electric heater was replaced by heat exchanger. In order for the heat exchanger to work, hot air was supplied to the heat exchanger at the shell site. Hot air was supplied at temperature of 465 degrees Celsius and at a flow rate of 500,000 tons per year. The flow inside the heat exchanger was set to counter current, and the performance of the heat exchangers was determined by hot stream outlet temperature, which is set by 350 degrees Celsius.